We started out with linear functions back in 10.2 it must have been. So all the equations were straight lines if you graphed it as a straight line. Then 10.3 we looked at quadratics, which is kind of, I think, one of your first introductions into parabolas. And those are all going to be either like U-shaped or N-shaped. Today's section is officially 10.4, and it's called Other Functions. We're just going to look at a couple different kinds of graphs, kind of a quick introduction to them. And as you go on and do stuff in algebra and algebra 2, you'll get a lot more practice with these. You'll do like a whole chapter, maybe 2 on quadratics, a whole chapter on lines, a whole chapter on exponential functions typically, things like that. So Other Functions is the title for today. And I'm going to start by looking at exponential functions. So exponential functions. And these look kind of similar to like half of a parabola, but the curve is going to be a little bit different if the truth were known. The key to an exponential function, what makes something an exponential, is that the variable has to be in the exponent spot. So before, quadratics were always like an x squared in there somewhere. Now we have to have something to the x power. The x is going to be in the exponent. So variable, typically going to be x, your independent variable, in the exponent spot. So that's what makes something an exponential function. And the generic equation for it is typically they do y equals b times x. And as you do this a little bit more in depth, you'll actually have like a number a times b to the x. But the key for now is just we have x in the exponent. And I should add where b has to be greater than 0. So you'll have some positive number to the x power. Whenever you do that, your graph is going to look like one of two things. So I'm going to do 2 graphs kind of side by side. And this first one is going to be exponential growth. If you have exponential growth, it has to get bigger and bigger and bigger, yes? So it's going to look something like this here. And this is why they encourage people to invest in their retirement when they're young, or start investing in like putting money away for college, like a long time before college. Well, that's hard to do. You're probably not making a ton of money. But a lot of people, what they do is they wait. They get out of college, they pay off their student loans, they buy a house, they try to pay off their house, and then when they get to be like 50, they start putting money away for their retirement. The problem is, I wouldn't mess up your graph, I'm just going to kind of get off track a little bit here, but if you take and start putting your money away right there, when you're 50, you want to retire 10 years later when you're 60, realistically, probably more like 15, 20. But that graph doesn't have a whole lot of time to go up yet, right? Where if instead you start putting money away when you're say back it up 10 years to when you're 40, well now 20 years have gone by. Do you agree you're starting to get to that steeper part of the graph? So now you have quite a bit more money that you could live off to retire. If you start investing when you're 30 or 25, you're starting to hit that steeper part of the graph still. So the key to investing money for retirement is to just start early. Because as you put more money in the bank, you get interest on it, and you get interest on the money you put in and the interest. You get interest on the money you put in and the interest. So it's kind of like you're getting interest on more and more money all the time. But okay, enough trying to brainwash you. You probably won't remember that in 10, 12 years anyways. But okay, moving on. So that's exponential growth. Do you agree my equation up here? What I'm really saying is I'm saying that equation is y equals, I wouldn't write this, but it's b times b times b. I wouldn't write this, but I have x b's there, right? So what kind of number, if I multiply that number by itself over and over, is going to give me a bigger answer? The number has to be greater than, if I do 0.5 times 0.5 times 0.5, greater than 1. So this here, the exponential growth, is going to be when b is greater than 1. And if you wanted to, you could say, maybe I'll just write a exp exponential growth. Now, exponential decay is going to be where it kind of drops off like that. And it shouldn't get too horizontal. Maybe I'll try to kind of do that last part a little bit. But it should start out steep and then get less and less and less steep as you go across. Now, b we know has to be less than 1, right, for this? And we set up above, right here, that b has to be greater than 0. So this is going to be numbers that are going to be between 0 and 1. So 0.5 times 0.5 times 0.5. If you've ever studied like half-lives in science class, that'd be an example of exponential decay. That's how they do like carbon-14 dating or potassium-20, I think it is dating. Moving on from there. So, okay, with this, I just want to throw an example out a second. So if I were to do, my example is y equals 2 to the x. So I have an example, y equals 2 to the x. I'm going to say this here for a story problem would be something like, this would be the equation if we have one bacteria on the sandwich that's left over from the Viking explorer tour yesterday. One bacteria on the sandwich. We'll say it doubles in number each day. So doubles in number each day.
Can you feel like each hour for a bacteria?
You could do each hour if you wanted to. This is a less aggressive bacteria. It's a weakened strain. But when you have that now, x is going to be the number of days. So then if you started out with 1, after 1 day you'd have 2, because you'd have 2 to the x. After another day it'd go from 2 to 4. After another day it'd go from 4 to 8. You're just multiplying by 2 over and over and over again, because it's doubling, which fits that 2 to the x. You have 2x times. You need to be a little careful that they're... so x could be hours, could be days, could be weeks, something like that. You'd have to change the units. But we could say then, how many bacteria do we have in 9 weeks? So bacteria, and I'm going to do a colon to save a little bit of writing. We'll say, we'll do days, 9 days. So how many bacteria do we have in 9 days? That would be y equals 2 to the 9th power. Now that gives me 512. So supposedly after 9 days, if nobody takes the sandwich home, there's going to be 512 bacteria on there. You with me so far? If we were to double that and say 18 days, it's going to be more than 512. A guess would be it's going to be about how many? We have twice as much time. Number of bacteria would be 1,024. Feels pretty logical, right? That you have twice as much time. But if we go back to our graph, it's getting steeper and steeper all the time, right? That would be 10 days would be the 1,000, because it doubles just in that next day. So this is a part of the exponential growth, kind of like the hole in your retirement. First 9 days, it only goes from 1 up to 512. If you're looking at 18 days, the equation is y equals 2 to the 18th power. Punch that baby in your calculator. It's not 1,024. It's 262,144. Because it's doubling on day 10, doubling again on day 11, doubling on day 12, doubling on day 13. So it's going up really fast. And that, my friends, is what your retirement can do. You get towards that end part. Okay, if we were to, we okay on this first example? Second example, we had termites in the tree behind and above our house. Kind of scary. Actually, no, we had carpenter ants there. We've evidence of termites in our house back in the past. But let's say we had people coming out spraying poison. So termites, maybe I should say carpenter ants, but whatever. Each spray kills 40%. So if we say each spray kills 40% of the nest. Now we need to be a little careful. If you think back to the percent chapter, do I do y equals 0.4 to the x? If it kills 40%, what do you multiply to figure out how much is left? Yeah, 60%. You're left with 60% every time. So what happens is it has to be 0.6 or 0.60 to the x power. That base has to be how many are left. And now x is going to be the number of sprayings. And if you think about it this way, maybe, I don't know if I'd write this in green, but try to tip you off. Say we start out with 100 of these termites. When they spray once, how many are going to be left? We kill 40% of the 100, so we kill 40, so 60 are going to be left, right? So to get that, it'd have to be your times 0.6, 60%'s left. And they spray a second time, and it's going to kill 60% of this, it leaves 60% of that original 60%. Does that seem to make sense logically?
Yeah.
Okay, so the b is always going to be the percent that's left. Okay, so then if the question is, so how many after 4 sprayings? Well, I mentioned before that the equation later on is going to be a times b to the x. And you're going to learn later on that a is going to be like the starting amount. So we're going to kind of look at it in this case as though we start out with like 100%. So that's just kind of like a 1 times this 0.6. So if I were to do 0.6 to the 4th, so y equals 0.6, 60% is left each time, 4 sprayings, I end up with a 0.1296. So this is, we're going to look at this kind of like a percent. So that's the decimal. What percent is that decimal? Yep, 12.96, or maybe I'll just round it to it. It's about 13%. So if I pay Orkin to come out and spray 4 times, 13% of those termites should be left, according to this equation, after 4 sprayings. Feel okay? So that's one type of function. That's the exponential functions. Any questions on those before we move on? You could, if you wanted to, for this exponential decay, you could make a comment somewhere that says, for decay, or if you wanted to, maybe when numbers are going down, b equals what's left after 1, or if it's a percent, you could say it's 100 minus that percent. That's going to be the decimal that you put in, or 1 minus the percent in decimal form. All right, the second and last type that we're going to do is going to be a step function. This will be a little shorter if you find your attention span starting to wane a little bit. This would be like how they figure out like parking garage costs and things like that. So step functions. We're not going to do as much equations for this as more just here's the shape and kind of how do you do a problem. But a step function, well, a function, one x value can't have 2 different y values, right? And if you think to a number line, if we wanted to say, I wouldn't write the number line, but if you wanted to say 4 and everything smaller than 4, we do a filled in dot shade to the left, right? That's x is less than or equal to 4. If we wanted to just do x is less than 4, we do the open circle saying like everything up to the 4 but not the 4, right? That's going to apply to the step function. To make it a function, we can't have one x value that has 2 different points for y. So the shape will be something like this. You'll have like a horizontal line typically, then an open circle on the end, and then directly above it we start with another one, open circle. Directly above the open circle start with another one, open circle, and so on. Once in a while you'll find that the open circles are on the left ends of the horizontal line, but that's less common. And kind of what's the point? Like you're probably thinking, how does this fit? Well, my wife and I, we went downtown to the Civic this weekend. Took our kids to see Alexander and the terrible, horrible, no good, very bad day. So we went to a parking garage, and for them, I'm just going to say they charge, we'll say $2 every half hour. And it's probably more than that. I'm just kind of making stuff up. So if we were to do this graph, time always goes on which axis? Independent, so it goes on the x-axis, so time will be down here. Because pretty much always, unless you're doing special relativity, time just keeps going at a constant rate. So we'll put that on the x-axis. And money usually depends on time, so money typically goes on the y-axis. And I'm going to make this fairly large, so I'm going to put a 1 over here and a 2 over there. And now my y values, let's do maybe up to, let's maybe go up to 10 or something. Or let's go to 8. So then my 4 is right in the middle, and I'd have like a 2 and a 6 kind of in there. All right. So now to graph this, when I first get down there, my first half hour I pay how much money? $2. So it doesn't matter, when I go in the parking garage, they're going to charge me $2 whether I pull in, I'm there for 1 minute and realize we left the tickets at home, like, oh no, and you quick drive to the exit, you're going to have to pay your $2 to get out. Up until like 29 minutes, 59 seconds, it costs you $2. So the graph then is going to be this horizontal line at my 2 until I get halfway to the 1, until I get to my, half of, I was kind of figuring time is going to be in hours. Maybe I'll put an H in parentheses there. And as soon as I hit that 30, so up to 29 minutes, 59 seconds, I'm paying $2. And then as soon as the clock clicks over that I've been there 30 minutes, at 30 minutes they're going to charge me 4. So it's going to be that dot right there. You with me? And then I keep paying $4 up until the 1 hour mark. And at 59 minutes, 59 seconds, I'm still paying $4. So you see people driving super fast down the ramp. But then once you hit 1 hour, you can do the open circle, because as soon as I hit 1 hour, I jump up to $6. They're charging me $6. And then for that hour to an hour and a half, it's a horizontal line again. I'm paying $6 till I hit the hour and a half. Then it jumps up to the $8. And $8 up until I get to the 2. Does that kind of make sense logically, how you get a graph like that from a parking garage? So you don't really have a nice equation for that. You'd have to have like a rounding function, and you'll get those later on in life. But typically now you'll just get story problems, draw a graph for the story problem. Any questions on step functions? Awesome.